Okay, so today we are going to be covering some more topics concerning sequences. So, like, we kind of talked about sequences in the second lecture, which was on convergence, but we kind of only defined like what a sequence is, and then we just talked about convergence. So now we're going to be talking about some more types of sequences. Um, and I think that's basically it. Um, so the first class of sequences that we'll be talking about are called monotone sequences. Um, and a monotone sequence has to do with essentially the progression of the sequence. And that is, suppose uh, we basically mean whether the sequence is increasing or decreasing. So if it is increasing, we denote this as x sub n with an arrow going to up and right. And this means that x sub n is less than or equal to x sub n plus 1 for all natural numbers n, right? So each next term in the sequence is always greater than or equal to the previous term. And similarly, we can define decreasing with an arrow going right and down. And this means that x sub n plus 1 will be less than or equal to x sub n for all n and n, right? So every next term in the sequence will be less than or equal to the previous term. And there are also strict versions of these. So you could see strict or strictly. So a strict increasing is denoted as x sub n with a just arrow going up. And this means that the inequality here is strict, right? So you can't have the possibility of x sub n equaling x sub n plus 1. It must be, there must be a strict inequality. These must be distinct elements. And of course, there is strict decreasing, which is denoted with a down arrow, and x sub n plus 1 is less than x sub n for all n. All right. And you can say that if xk is increasing, then the sequence xk goes to its supremum. More precisely, the supremum of the set, which consists of all the values of the sequence, right? Now recall that supremum of s equals infinity, if S has no upper bound and x sub k goes to infinity is a special case of divergence. Right? In particular, it's divergence to infinity. And we defined what this notation means, right? This is just notation because infinity is not a real number. This is just notation saying that the x sub k are getting more and more positive. They're increasing without bound, right? And that makes sense if the sequence x sub k is increasing and the set of all the values of x sub k have no upper bound, then it makes sense that the sequence is just going to keep getting bigger and bigger without bound, and so it's going to infinity. Of course, you should write down the precise proof for that to get a feel for it. But if we ignore that case, then the case where x sub k is not a bounded sequence, right? If we say, or basically, if we know that, what should I say? If we know it is bounded, right, then we know that this has a supremum, and therefore we know the sequence has a limit. So if a monotone, oh, and also, of course, you could also, if x sub k is decreasing, then x sub k goes to the infimum, right? And again, with the infimum, you might have negative infinity. So if a monotone sequence is bounded, it converges. Sorry, it converges. And notice this is not the case for a general sequence, right? Because you could have a bounded sequence that oscillates, right? Say between 2 points. Clearly it's not converging, but it is bounded, right? But we do know in general, convergence implies bounded. And therefore, a monotone sequence converges if and only if it is bounded. Which is kind of a nice little result. Okay. The next thing we can talk about is arithmetic of sequences. So, suppose I have two sequences, x sub n, which converges to L, and y sub n, which converges to M. then the sequence formed by x sub n plus y sub n converges to L plus M. The sequence formed by multiplying x sub n by some real number C converges to C times L. The sequence formed by multiplying x sub n and y sub n converges to L times M. And the sequence formed by dividing x sub n and y sub n converges to L over M, where in this case we have to assume y sub n, the sequence y sub n is never 0 and m is not 0 as well, right? In order for these divisions to actually be real numbers. Now, these proofs have some helper results that you should prove first. The first is that x sub n converges to L if and only if x sub n minus L converges to 0. Which again seems kind of silly, but and the proof isn't hard, of course, but it can save you some steps in a proof if you use this result. And another one is if S sub n converges to 0 and T sub n is bounded, then the sequence formed by multiplying S sub n and T sub n converges to 0, right? The idea here is that since T sub n, right, T sub n is going to be contained in some finite interval, and then as you keep multiplying by numbers that are getting closer and closer to 0, those will eventually beat out the upper and lower bounds of T sub n, right? The only way this wouldn't go to 0 is if T sub n was going towards infinity, in which infinity and 0 would sort of fight each other. Of course, I'm speaking in not rigorous language there, but just to give you a picture. So, like, this result should make sense, basically, is what I'm saying. So yeah, you should go through the proofs of these 4 statements, and you should prove these first two. You should prove these 2 things first, and then go through these proofs. And these are going to give you a taste of sort of the epsilon delta feel, right? You have to say, you have to let epsilon be greater than 0, and then construct the corresponding delta, which is going to, or not delta, sorry. I guess these would be epsilon n proofs, rather, where you have to show that for n large enough, you can get within your bound. In order to do that, you can use the epsilon n definitions of these sequences, which you already know converge. You already know there's an n for some number, right? So the trick is always going to be that you have some epsilon, and then you break it or you use that epsilon to construct some other epsilons, which you use for these limits. So say you start with an epsilon here, then you have an epsilon 1 and an epsilon 2. Say you won't always need two of them, right? Especially here, right? You only need epsilon 1. But these epsilon 1 and 2s give you values n1 and n2, and then you could take the maximum of these two numbers and let that be n. And then you could usually work from there. The next thing, which is going to be helpful, or not really helpful, but just some definitions that are used in analysis. So let n sub k be a strictly increasing sequence in n, right? So we have a strictly increasing sequence of natural numbers, right? The natural numbers themselves form such a sequence, right? 1, 2, 3, and so on. But this could be like 1, 3, 5, or just anything as long as it's strictly increasing. Then we say x sub n sub k is a subsequence of x sub n, right? And so notice this sequence here is indexed by k, right? Because k is the index of our sequence of natural numbers, and so that's going to be what's controlling this subsequence, right? So say, right, x sub 1 is like x sub 1, or sorry, x sub n is x sub 1, x sub 2, x sub 3, dot, dot, dot. And then suppose like n sub k is like 1, 2, 4, 8, right? Like powers of 2, for example. Then x sub n sub k is going to be x sub 1, x sub 2, x sub 4, x sub 8, and so on. Or you can write this as x sub n sub 1, x sub n sub 2, and so on, right? Because we know this is n sub 1, n sub 2, n sub 3, and so on. Alternatively, there's another way of expressing subsequences, which is to let me write alternatively. You could let phi of k be a strictly increasing function. So if j is less than k, then phi of j is less than phi of k. Then x sub phi of k is a subsequence of x sub k, right? So to relate these examples, you could say phi of k is like 2 to the k minus 1. And those would give you the same examples. And the only result here is that, or that we're going to talk about in this lecture, is that if our sequence x sub l converges, or sorry, x sub n converges to L, then every subsequence converges to L, right? And this this can often be useful in the reverse direction. Thus, if two subsequences have different limits, or if one of them doesn't converge at all, then x sub n does not converge. So yeah, that's it for this lecture. Do you have any questions?
Okay.
All right, that's it.